Yeah. So I'll reintroduce the title because it was about 5 minutes ago. So known good dies at the heart of a sustainable open chiplet business model. So we'll talk a little bit what that is. Just quick introduction, Roberto Rotilli. I work for Teradyne, and I've been at Teradyne for the last 16 years in different roles. I'm mainly focused on semiconductor test. Now, what we mean by known good dies at the heart of a sustainable, open, heterogeneous chiplet model is exactly that. What we're going to do in the next 15 minutes is kind of explore the impact of KGD with a simplified business model and holding a lot of variables constant with the exception of KGD. And what we're going to look at is there's really two parties that are responsible for a transaction in an open chiplet model. It's the party that's supplying the chiplet, and then there's the party that's basically aggregating the chiplets and then selling it to whoever the end customer is. And so we'll explore those two business models, of course, and the impact, and then we'll converge on really what is key, which is a high-end predictable KGD. And then we'll discuss some of the challenges in order to achieve it in a chiplet environment, and of course, some solutions. Now, what we'll do is we'll kind of go back to square one to get everybody grounded, which is really what's the manufacturing and test flow, very simplified. We'll get a more complicated one in some of the other discussions further on, from a monolithic piece of silicon, and then we'll compare it to really an open chiplet model, and then we can kind of describe some of the differences and why KGD is likely more important. So really, you start with the fab, you get the wafer, you do wafer test, you pass the good dies, you fail the bad dies, so there's a scrap cost that's incurred, which is the cost of the die. Then you package the part, and then you do a package test, and then the ones that fail, you scrap those, and really what you're burdening is the die cost, of course the test cost, and the packaging cost, which relative to the die is far more expensive. And then you get into this binary, it's very simplified, you get into this binary flow, which is you ship it to the end customer or you do a system level test. And system level test is generally reserved for more complex SoCs where there's a ton of IP blocks that are interacting with each other. Now, of course, like I said, it's simplified. You still have burn-in, you get QA, there's a ton of other steps along the way. But the goal is to keep it simplified, to illustrate a point. Now, when you look at a chiplet-based SiP heterogeneous solution, it's a little bit different, right? You end up getting, you get a ton of wafers, right? Each wafer will have its chiplet. You test those, you pass the good ones, you fail the bad ones, you throw out the scrap, then you assemble to a substrate, you test that. But then really, as you're going through the process, you're aggregating these chiplets. And in most cases, you're aggregating more IP than you would with a monolithic SoC. And every time you're failing it, you're throwing it out, but you're throwing out not just the packaging cost and the die cost, but all the other chiplets that come with it. And we'll see in an open model, it's not just the cost, it's the price that you pay if you're the builder. And then, of course, once you assemble it all onto a substrate, you do a test, and then you're most likely, there's not this binary option, you're most likely doing an SLT insertion. Because what you'll have is you'll have a lot of these chiplets that will have a standalone IP block. There's a lot of dependencies between them, and when you put them all together, you're going to want to stress that. So the takeaway here is KGD and quality gets really pushed even further upstream in a chiplet model. Now, we're going to go look at two parties, and it's a simplified business model. And the first one that we're going to look at is the chiplet SiP builder. So this is the party that basically buys chiplets from the providers, and we'll look at their business model and aggregates them onto a SiP. Now, to illustrate a point, we took an ODSA POC concept. It's just a simple chiplet, right? You've got an FPGA, a CPU, a network processor, and 2 DRAM. And what's important is looking at the chiplet cost. So if you're the builder, you're procuring these chiplets at this cost. And so if you sum it all up, it's about $48. Now, at the bottom, it's a simplified margin and profit table, right? Like I said, we keep it simple, but we're only looking at one variable to illustrate a point, which is KGD. Now, you're assuming you're getting these chiplets with a KGD at 98% from your chiplet provider. Now, is that a high number or a low number? It all really depends. We picked 98% to illustrate a point, and there's some challenges getting close to 100, as we'll get into. you've got 5 chiplets, right? And then just as you put them all together and you aggregate them, just based on KGD, you're going to basically get a 90% yield. So you're going to get an 8% yield drop. This doesn't include the yield due to assembly. Once again, we're keeping it simple. We're isolating it to one variable. And so what does that mean? Well, for a $48 chiplet, you're basically, every time you build one, on average, you're throwing away $4.61, just based on KGD. And so if you assume your SiP cost is 48, you're going to sell it to the market at 96, whoever that market is. You're about a 50% margin, and your scrap cost is going to basically drop your margin by 5%. So KGD is clearly has an impact here. And if you kind of do a sensitivity analysis on KGD, you can think of it in this example, right? Simplified example. A 1% change in KGD has a 2.5% contribution margin impact. And of course, if you take a look at the math, is every time you add a chiplet at a specific KGD, the probability of that SiP failing goes higher. So in this example, every chiplet you add reduces your margin by 1%. Now, so now what does that mean? So if you're wearing the builder hat, so you're the builder and you're buying all these chiplets, what's important to you? Well, KGD, high and predictable. What's also important is if you've got the clout in any negotiation, you'd like to structure a clause in a contract with the chiplet provider for them to be responsible for scrap cost, anything below the yield that they're committing. And then, of course, as a chiplet provider, you'll want to, as a builder, you'll want to provide as many chiplets yourself, or at least a few of them, because the scrap cost is now measured in COGS versus the price with which you pay it. And then, of course, you also want to balance the right number of chiplets, because as you've seen, the more chiplets you add with the KGD, there's a multiplier effect in terms of a yield loss. So I think to have some fun and to explore maybe one of these options, let's assume you're now a chiplet provider, so you're selling the chiplet, and you've signed up a clause with the builder around scrap cost, meaning anytime you have a yield deviation from your pre-negotiated KGD value, let's say at 98%, you're going to be responsible for the entire scrap cost of the aggregated chiplet. So that's this business model. And to stay true to the example, we still got the ODSA chiplet there. The table on the bottom, you can think of it a couple of ways. Maybe the simple ways you can think of it as there's 4 companies providing chiplets to the SiP builder. And let's start with the one who's providing the FPGA. As in the previous example, you're basically selling it for $10. Your cost as the provider is $2.50, and your margin's about 75%. So you've got into this contract where you're responsible for scrap cost. You've negotiated a 98% yield. The actual yield that they're able to prove in the field has gone to 96%. So there was a deviation, a yield excursion. And now what's happening is it's really yielding at 96. So you're now liable for the scrap cost. So if you're the FPGA provider and the SiP is $48, you're basically paying $6.54 out of your pocket for every one of these chiplet SiPs that are being shipped, so long as you haven't gone back up to the 98%. So what does that mean? That means a 10% margin loss. That really hurts the bottom line. If you're the CPU provider, now you're providing the more expensive chiplet in the SiP at $20. It's a 5% margin loss because the scrap cost is less because you're. And then, of course, if you're the DRAM where you're the $4 chiplet in this $48 SiP, your profit pool is a lot less to pull from. If you have a 2% yield excursion from your negotiated 98%, you're basically taking a 24% margin loss. So what are the key takeaways? Well, if you're the chiplet provider, once again, you want KGD to be as high and predictable as possible. You want to avoid these quality contracts. And if the clauses do exist, which for whatever reason you have to sign one of these contracts because it's good business, you want to be providing the high-value SiP. And then, of course, the other thing you can do is really sell untested wafers. So you're just basically selling the wafers and you're putting the burden and the testing back onto the chiplet provider. Now, So the one commonality is KGD, but between the chiplet provider and the SiP builder is you want KGD to be as high and predictable as possible. Well, it's easier said than done when you're talking about an open model. And so if you look at a monolithic package, you can do a lot of different testing before you ship it to whoever is going to integrate it into some MCM, or they're going to integrate it into a PCB. But if you're selling the single chiplet, really your ability to have test coverage is reduced, right? You can do your wafer sort test. You can't do your final test. It'll be difficult to do hot and cold testing on a wafer sort insertion. We've talked about die-to-die interfaces. These are short, high bandwidth wires. They don't have most of them don't have the signal drive strength to drive off chip into an ATE. So you're really not getting a ton of testing done on the die-to-die interfaces. You're doing your DFT, maybe you're doing your BIS, but it's certainly not going into an ATE. And of course, you're not doing system level tests if you're providing the sole chiplet. And then of course, there's the burn-in, right, to catch latent failures through thermal stress testing. So what can be done, right? We've talked about KGD being incredibly important to both parties. It should be high, it should be predictable, yet there are some challenges associated with that. Well, there's no panacea, there's no one solution that addresses it, but there's a lot of ideas that are certainly being thrown around in this community and are being thought out through a lot of the leaders in the industry. So of course, adding design redundancy to the chip is something that's very common and what a lot of people are doing, which is any parts of the chip that has a high fail rate, you can repair it on the fly. So adding extra cores, adding extra wires for your die-to-die interface, extra memory banks, so on and so forth. Of course, it all comes with a cost because you're adding more pieces to the silicon. You can also, if you're the provider, right? So you're aggregating all of these chiplets. So you're the builder. You can test it as you build up the chiplet, and you can put the chiplets that are most likely to exhibit high failure rate. Throughout the assembly process, you can add the chiplets one by one and do testing. And so when it does fail at that point, you're at least not throwing away all the chiplets, so you're minimizing your scrap cost. And then of course, order matters on how you do that, and it really has to be specific to the process. And then of course, you can consolidate really to how many suppliers you're picking from in terms of the open model and really buying pre-combinations of die, of sub-assemblies. Now, what's the call to action? I've got 2 minutes here before I get booted off stage. So, I've got the model, right? There's a model that we worked on. Like I said, it's simplified. It really isolates to one variable. And that's a model that I'm going to share on the ODSA drive. So a call to action is, of course, if anyone's interested, if they can poke around in the model and provide some insights where we can make it slightly more complicated and more nuanced would be helpful. If anyone's got some great ideas on how to make KGD more high and predictable in an open chiplet model, is certainly something we would be interested in having them part of the group. And then of course, quality contracts have existed since the beginning of time. They exist today. And if there's any quality contracts that anyone is aware of that would address a lot of these problems, it'd be very helpful if you bring it to the table and to the discussion at OCP. Thank you.
Does anyone have any questions?
Hi, I have a question.
Yes.
Okay, my question is about basically going to the chiplet with advanced package for 3D integration. It looks like with advanced package with micro-off, we're going to get basically smaller Bruno die. How do you see basically the challenges for that one? Some of the application also comes with the micro-off.
Yeah, so the question is, just to maybe repeat it, is as we get to advanced packaging with 3D stacked die, it's going to be more difficult to get to KGD.
Yeah, and do you see that it's going to affect the chiplet ecosystem, or something that you have to do?
Yeah, I think it goes back to the heart. I think it's going to make it obviously more challenging in an open model. And it's, I think there's no answer to other than if you're the provider, meaning you're providing the chiplet or you're the builder, I think you've got to really have a solid set of legal contracts and or testing to get a high predictable KGD, or else both parties could be at risk financially.
I had. Okay, it's not working. Can you hear me?
I can hear you though.
Okay. If the KGD yield is wafer lot dependent, then one idea you might consider is to do a lot acceptance test on your chiplet lot, do a sample assembly
Check.
at lot, make sure the yield is good before you commit the whole lot to your KGD flow. Something I thought of, like
Yes, I think that's a good idea. Certainly if you're the chiplet provider, before you're, but I think that the challenge is, do you have a lot of confidence in that screening at the wafer lot?
at least you'll be able to know. I'm saying do a sample assembly of that wafer.
Oh, right. Yep.
Do a lot acceptance test by doing a sample assembly,
And then ship.
getting approval from the end customer. Hey, do you accept this lot based on these test results? Yes, we accept it. You hit your yield target in the sample assembly.
And then you ship the rest of the bank of wafers.
The entire wafer lot.
Yeah,
I think this is a really good idea. So it's a way to build more predictability into the yield of the chiplets. Rather than committing the whole lot and start building these large multi-chip modules, and you see you're only getting 95% yield, 90% yield, and then everybody's pointing fingers.
Yeah, I think that's a really good idea. Thank you.